Hi. Yep, so welcome to MFA the Right Way. My name is Collin. I'm an engineer at a Manhattan-based data analytics company called Predata. We help clients answer questions about geopolitical events by building models of what we call digital concern. We're a Django shop. We love Python. We're growing really quickly right now, so if you're interested in geopolitics, machine learning, data visualization, or data engineering and infrastructure, please come find me around the conference. I would love to talk with you. Yeah, I've been there 4 years. I love it, and we have a fantastic team. So now, with the plug out of the way, we're here to talk about implementing multi-factor authentication with one-time passwords in Django. There's going to be a little bit of code, not a lot. And if you miss something, don't worry. You can find it all on my GitHub, or you can, which my name is Cronian, or you can go to this link. Just to bring it back up, that's my GitHub if you want to find it. Yeah. So before we dive into the meat of this talk, though, I think it's worth taking a minute to reflect on how far we've come in terms of computer security. Like, it's 2018. We're designing with security in mind. We're learning from our past mistakes. And so companies are doing a better job of protecting our data, or at least the major companies are. And of course, your engineers are auditing code and not running untrusted code in production. Of course, you can trust your hardware. And your end users are finally security savvy and helping you out. Two of these headlines are from the past week. One was from yesterday. So this is unfortunately not, right? Like, I think there are a couple of important assumptions for us to make before we move into the real meat of the talk. One is that security is still clearly hard in practice. Like, when I say hard in practice, I mean individually, maybe each of these decisions that you're making aren't that complicated, aren't that hard to get right. But collectively, all of the little things that you do that have security implications all the time add up. And it's more than what you can keep in your brain. At this point, in order for us to be secure, we really need process to make sure that things aren't slipping through the cracks, that you're staying up to date, and that you understand what other dependencies you're trusting. And so the fact that these things are still happening at major companies, I think, is an indicator that it's just really difficult to get this process right. And I don't think that it's necessarily negligence. I think it's just the result of an inherently complex system. So two, I think eventually somebody's going to leak password data. Hopefully nobody in this room. It could actually be your end user in a phishing attack. And when passwords do leak, they'll probably be reused elsewhere. And that's just because people don't want to have, it's difficult to manage too many passwords. People don't have a good process for it. And so as an aside, if you haven't done so already, I highly recommend that you check out haveitbeenpwned.com and just put in some of your email addresses, see what's already out there about you. Like, you may be surprised. I think I purchased Photoshop a few years back, got pwned by that. So yeah, I would highly recommend that you see just how much data is leaking. And so then what can we do to make sure that our users aren't going to be compromised on our service when we can't trust that other third parties or the end users themselves are going to leak information, login information. So rather than depending on a single potentially shared piece of information, why don't we depend on several different pieces of information, hopefully independent pieces of information that can't all be compromised the same way. And so that's basically the premise behind multi-factor authentication. So we're going to use several different pieces of evidence of identity called factors, typically from different sources. Something you know, like a password, something you have, like a key, or something you are, bioinformatics, like your voice, your fingerprint, retina scan, face. In this talk, we're going to be focusing on your password as before, an additional key called a token. OK, so let's dive into that. Token-based one-time passwords. So what is this token? Well, it's just some long, random secret string. And it's known on the server side. These are your server racks, I guess. And it's known on the client side. And on the client side, it could be stored in software on an existing device like a cell phone, or it could be on a dedicated hardware device. And we're never actually going to send the token to the server. Instead, we're going to use some algorithm that takes the token in as an input and is going to generate some random one-time password that we're going to send along with our normal password to authenticate on the server side. And every time we run this algorithm, every time the client wants to log in, we're going to generate a different OTP each time, one-time password. And the client sends it to the server. The server generates the one-time password with the same approach, confirms that they match, and then everything's good in the world and we can log in. And so this is great because now the user isn't immediately pwned in the event that their main password is compromised. And the information that we're using to log in isn't stored by a third party. It's only stored on our server side and on the client side. Obviously, if attackers have access to your server side, you already have major problems. So really, we're concerned about the client side getting compromised in some way, that the device gets lost or stolen, or that the user gets tricked into revealing a one-time password. And in the event of a physical device like this USB fob, it might not even be possible to install or very difficult to install additional software on the device to steal the password. So again, we're really just concerned that this device is going to fall into the wrong hands. Also notice that we're not talking about the form of MFA you're probably most familiar with, which is some SMS, some text message being sent to you with a one-time PIN. And I'm not going to say that you shouldn't use that, but in this case, the thing that you have is your cell phone number. And the assumption that that cell phone number is yours and can't be stolen is actually probably not a good assumption, that it's possible for attackers to trick your service provider into forwarding your number to them. And this has happened in practice. So if you're really, I think that it's easy enough for us to assume that all of our end users are going to have a cell phone if they're getting this text message anyway. So we should probably just not use that approach. All right. And so in practice, this seems to work pretty well. So earlier this year, Google announced that since they started requiring all of their employees to use hardware keys to log in, that they've had 0 successful phishing attacks in about 18 months since, I guess, the start of 2017. So it seems like this is actually effective. So earlier I mentioned that we're going to take in this token and we're going to run some algorithm and we're going to get a different output each time. So you might be able to guess that whatever that algorithm is needs to have other inputs besides just this token. So we have some other input. And we're going to generate different numbers each time. So what could this input be? Well, if you have any background in cryptography, you might notice that this looks very similar to a keyed hash function, and that's basically exactly what it is. So the token is the key to this hash function, and we're just going to pass a different message in each time to get a different output. And so that could be as simple as a counter. We could just increment a counter with the same key for a hash function, and boom, you have HOTP, HMAC-based one-time passwords defined in RFC 4226. So that's one common choice. The second choice is very, very similar, but instead of having a counter as the input, we're going to derive the counter based on the time. So we're not literally putting the present time in, but we're doing some basic operation on the time to get, again, a counter like 0, 1, 2, etc. And time always goes up, so our counter always goes up. And this is TOTP, time-based one-time passwords, RFC 6238. And just to compare, because I think the naming is a little bit confusing, they both use hash functions. You might think HOTP, oh, H is hash, so that one uses hashes. They both use hashes. The actual difference is that HOTP uses this counter that's stored in memory, and TOTP takes the time to generate what the counter should be. It's actually typically SHA1 that's defined in the spec. So if you are security savvy, you might be taken aback by this, like, oh my god, that's a hash function that is no longer secure against collisions. This is actually not a problem. If we have time at the end, I'll explain why it's still secure. All right, so let's go through an HOTP example of how this works. So initially, we have the token stored on both the client and server side. We have some other state as well, like the current value of the counter, and then just some number of digits that we're going to expect the one-time password to be, some length. And the user is going to click on their click on their device. We're going to increment the counter. We're going to pass the token in the counter into our keyed hash function, get out some long hash value, truncate it to the number of digits we want, and send that to the server side. And the server is going to do the exact same operation, increment the counter, do the same math, get the same value, and confirm that everything checks out. So this is good. The problem, though, is if maybe there's some issue with the network, or somehow you manage to click the button on your hardware device and you increment the counter, but the server never finds out, and now you're out of sync, and every time you click this button, you're sending a different value, or you're generating a different value, and the server doesn't get the same result, and now what do? The typical solution to this is we just add a window. We say, actually, we'll check the next 50 iterations of this operation. And if we find that we match on any of these, we will set our counter value on the server side to what we believe it must be on the client side. And now we're back in sync. Everything's good in the world. And this works pretty well, assuming that your end user doesn't do this. And this is actually a problem. Like I haven't tried this recently, but and I don't recommend you try it, but you can take a lot of car keys, go out of range of the car, just go to town on the button, click it 50, 100, 200 times. You're going to make that key no longer work. You'll need to use some mechanism to get the key back into sync with the car. So yep, that's all there is to HOTP. TOTP is very similar. The difference is that now we don't have to worry about this counter. Instead, we have some value called a time step. And when the user decides that they want to generate or find out what the one-time password value should be, all they do is they take the current Unix time, which is just some number of seconds from the start of the Unix epoch, which is the start of 1970. And we divide that into some number of time steps. You can just set what the size of your time step is, typically 30 seconds or 60 seconds or something like that. And yeah, we use that number of buckets, time steps, as the counter. Then everything after that is the same. We pass it into our keyed hash function. We get our output, we truncate it, we send it to the server side. Server does the same operation, and as long as our clocks are more or less in sync, everything's going to check out. If our clocks are a little bit out of sync, or the request takes a little bit of time to send, we could end up in a position where you generated the one-time password based on the last time step, and the server gets the value based on the next time step. But in this case, again, we can do something very similar to our window approach from HOTP. We'll just try the past couple of time steps to make sure that there wasn't some lag in receiving the input from the user. And there's nothing to keep in sync here other than our clocks. We just assume that we both have a means to have an accurate view of what the present time is. So now again to compare, with HOTP, one of the downsides is that you can increment this counter and get out of sync potentially. But with TOTP, we shouldn't fall out of sync, again, as long as our clocks are pretty accurate. HOTP, though, does have some advantages, like you don't need a device with a battery to run this. Like you may have like a YubiKey USB fob. That's an unpowered device. It just has a little bit of memory, and you plug it into your computer, and it draws the power it needs to run this really simple circuit and generate the output. With TOTP, you do need power because you need to keep time, and you probably can't rely on the device that you're plugging into to tell you what the time is. That could potentially be an issue if somehow you plugged into a malicious device and it told you that it's actually some time in the future. And so in addition to not being able to log in, you could potentially generate one-time password values that would be valid in the future and steal those and then later on attack the user. It's assuming that you're plugging into some untrusted device, but I guess it's possible. All right, so this is really all there is. I promised that there would be a little bit of code. The code is quite simple to set this all up. This is really the core of it, and then I'll show you a view in Vim where it should be a little bit easier to read. But the heart of this is really just this section here, that in Django, we're going to store the user's secret token in the database, use it to initialize our TOTP algorithm that we've imported from the PyOTP library. Then we're going to get the value of the one-time password that was passed into our form, pass it into this verify method. We have some window just in case there was some input lag, network lag. And we're going to get back true or false. If true, then the form cleans, everything's valid, and we can go ahead and log the user in. If it's false, then throw some validation error, tell the user that the input was invalid. So let's go through a quick demonstration. Hopefully all my styles don't break. Great, looks OK. First, I'm just going to give you a demonstration of how this works. So I'm going to go ahead and log in. Star Wars. Log in. All right, hello. So I didn't have MFA enabled, but I'll go ahead and go to my profile page now and just click the button, say that I want it, pull out my phone, go ahead and scan. I'm using Google Authenticator, but there are a lot of options here, Authy. Cool. All right. Log out. And let's try that one more time. My bad password, and our one-time PIN. All right, great. And just to demonstrate that that I of course can't log in with something invalid, which would be silly, and similarly, this one-time PIN needs to be valid as well. All right. So cool. That's an end-to-end demo. Let's look at the code for that. And as I mentioned a second ago, the code is actually quite simple. Whoa. Hopefully that's readable. Is that OK? Great. So all I did here was I basically spun up the Django starter code that you would get whenever you create a new project. And these are all of my URLs. This is my entire URL conf. This is the base page, login, an additional page if there's a second step to your login. If you have MFA enabled, log out, and then this profile page where we can turn on or off multi-factor authentication. To look at the views that back that, here they are. This is all of them. So what I've done here is I've taken the login view that Django provides, and I've subclassed it to change form valid, which this login view takes in a form, and if it's valid, it basically just runs the Django login function, which takes your anonymous user, turns it into the user based on the credentials that were passed in, and then after that, your session will continue to have this user associated with it. In this case, the difference is that I first check if you have this OTP secret saved in the database, and if you do, I'm not going to just immediately log you in, and here's the login function. It's a Django built-in function, Django provided function rather. Instead, I'm going to put some information in the session for the anonymous user. And I do that because I'm going to need to access it on the next page when you type in when you pass in your PIN. And here I'm just redirecting to the page where I'm going to ask you for that PIN. That view is right below. So here's the OTP view. All I'm doing here is I'm using this form. That was the form that I showed in the slides, and we'll look at that in a second just to see it again. But again, it's really pretty simple. What we're going to do is check if the form is valid, and if it is, we're finally going to run login. And if it's invalid, then we'll go ahead and redirect you back to the start of both login pages to ask the user for the username and password again as well. And yeah. And then there's a profile view. There's nothing really special about this view. It just, in the event that the user checks that box, I want to enable MFA, we go ahead and we generate a random secret for them and store it. That's basically all that happens in this view. Really quickly, in case you're wondering how I am storing this information in the database, because Django is sort of notorious for not making it easy for you to modify the user model. I'm just using the approach of having an additional model called profile with this one-to-one field on the user model instead of trying to hot swap out the Django provided user model. And I have this receiver post save anytime a user is created. I make sure that there's a profile object for that user. And there I can just go ahead and register whatever additional fields I want. So with an additional join, I can go and get that secret. All right. And then here's the final piece, that form. Oop, there we go. Here's the char field. We're asking for this one-time PIN. and clean is where the magic happens. So before we had the user PK stored in the session for the anonymous user. We pull that out here, make sure, of course, that there is a user PK and that that user actually has MFA enabled, just sanity checking. And then here's that same piece that we saw before. We use that secret to initialize the TOTP algorithm, pass in the value of the OTP field in the form, make sure that it's true. And if it's true, we go ahead, we clean, and as you saw before in the form valid function in the view, we'll go ahead and log in. So that's it. I think we have a little bit of time left, so I'm going to give you, I promised that if we had some time left over, I would talk about why we don't need to worry about SHA1 collisions. So I'm assuming a little bit of familiarity here with how hash functions work, but broadly speaking, there are more inputs than there are possible outputs because your hash function is taking the entire set of all inputs and truncating it down to some number of output bits. That's just how hash functions work. In our input space, there's some pattern in how these inputs are being incremented, right? We have the same secret each time, and we're incrementing our input. So there's this pattern in the input space. It's producing something in the output space that looks random. And it is totally possible now in SHA1, with SHA1, that we could find another input that hashes to the same output in the output space. However, this doesn't tell us anything about the pattern. This doesn't give the attacker any information about, OK, I found this one collision, but how do I then go and find another input in the input space that's going to produce a collision with the next output in the output space? And this pattern is known to the server and the client, but the attacker has no access to this even if they manage to find one collision. And the reason for that is the collision they find may have a different secret input value. I suppose they could try to take that input value and just go ahead and increment that on the off chance that they actually find the right secret input pair, but that's presumably very unlikely, hopefully. And yeah, that's it. That's how the security of HMAC works, even with the collision, no longer the guarantee of collision resistance with SHA1. I don't know if we have time for maybe one question, but that's all I have, so happy to answer any questions you may have. Yeah.
Is it like a library that you use for
Yes.
verifying? Yeah.
So the library that we're using here is PyOTP. You can see it here. Or it's also in the description of it's in the talk name. But yeah, PyOTP. There are other libraries out there that are going to hide more of these details from you, but I picked this one because it really goes all the way down to exactly the base level of how this algorithm works. So I think it's good for educational purposes. But you could do other things in Django that abstract more away. Yeah.
Real quick side question. So in your back and forth, you generated a QR code that you could scan with your authenticator. Does the library support the ability to generate those QR codes, or is there something else you're using for that?
Yeah, sorry, that's a great question. So the library produces no, it doesn't. It produces a string that you can put into another library. It's just a QR encoding of that string. That library is called Curious, Q-R-I-O-U-S, but there are probably a lot of options. All right, oh, one more.
How'd you get back into your car?
Oh, yeah, it wasn't my car, so I don't know.
How long did it take you to explain that?
Yeah, thankfully I think there was another key, but a lot of cars, I'm so sorry about that. I think a lot of cars actually do protect you here. As long as you can get back into the car, there will be tricks like you turn the ignition 2 times after clicking the button on your, fob like 10 times. Some weird, esoteric trick that you can use to get the key in the car back in sync, if that does ever happen to you. All right, thank you so much.